All right, we're in Parallel World again. Stephen Toub, how you doing, man?
I'm doing great, Charles. How are you?
Good. So you've been kind of busy for the past year or so working on Async.
Yeah, it's been a lot of fun.
And you've been on Channel 9 a lot. You've talked a lot about task and task-based parallelism. The interesting thing here is this is task-based async as opposed to task-based parallelism. Talk to me a little bit about that and about what exactly you've done and the relationship between task and async, and then we can get into some more details.
Right. So when we started with the task parallel library, initially as CTPs, we had some stuff from Microsoft Research. It came into the parallel computing platform team. We brought it into .NET 4. Task started its life really all about parallelism. It was a mechanism for you have a big problem that you want processed, and so you break it down into little pieces, run all those pieces in parallel, and join them all together, kind of typical fork join stuff. And it served as the basis for parallel loops and p-link and so forth. But what's interesting is as you kind of watch the evolution of task from when we first kind of conceived of it at MSR and then brought it into the framework and evolved over multiple CTPs and betas, is slowly but surely it stopped becoming just about computation. And its API surface and its functionality evolved more and more towards it being able to sort of represent any arbitrary async operation. And in fact, when we finally shipped .NET 4, if you hover over task and you see an IntelliSense or the little tooltip that comes up, its description represents an asynchronous operation. And that's sort of fundamentally what it is. And so people still, because of the early days, think of task as being this thing focused on compute. And it's still great at that, but it can also be very much focused on I/O or any other kind of async operation. And in fact, one of the types that exists in .NET 4 is this type called task completion source, where you create one of these and you just get its task. Nowhere is a thread created. Nowhere are you launching any work items. All you have is a task, and all it is a data structure that you can pass around like any other task, and then you can manually resolve it. So you can say task completion source .set result or .set exception or set canceled, and anyone consuming that task sees it like any other, just as if you had called start new. You have a task that represents this operation, and as a result, you can take any kind of asynchronous operation you may have and just put a task facade on it. So task really does become this kind of universal representation of an asynchronous operation, which is sort of what leads into all of this work we've been doing with the language C# and Visual Basic support for Asynchrony. We've been working on this for a long time now, and a lot of the ideas for it actually started in this team as well with Nicholas Gustafson's work on Axum, for example. So if you look at Axum, one of the main things that it brought with it was this compiler transformation, this rewrite that allowed you to take a method, write out sort of a synchronous looking operation, but the compiler automatically would see, oh, I see you're calling stream.read. I'm going to translate that automatically into begin read and end read and so forth. So the language work sort of started from a proposal based on that, and with a large working group that spanned people on this team, people from the Visual Studio team, the languages team, and from teams across the company, kind of looking at what's the right way to bring this into the language. And slowly but surely we evolved to a point where we have this task representation in the .NET framework already that is really kind of, if you look at academic literature, it's really just a future. And that's exactly what the language needed in order to be able to represent, both produce and consume these asynchronous operations. And so that's where the language has kind of settled. When you write an asynchronous method, you're producing a task or a task of T result. And when you await something, one of the primary things you can await is a task or a task of T.
Excellent, man. And so this is an example of not just a excellent cooperative working group amongst divisions, but you have an idea from research that has finally found itself way in front of developers in the form of a couple new constructs in a language.
And I should mention not just research from the perspective of the task parallel library, but also Don Syme and his work with F#. So in F# you have these things called asynchronous workflows.
Yes.
And there was a lot of great pioneering work that was done there to introduce asynchrony into a mainstream language. And so you can also look to F# for a lot of the inspiration, almost as sort of a leading the way for the behemoths that are C# and Visual Basic that have been around for a lot longer and thus have to be a little bit more cautious about what they put in.
Yeah.
Whereas something like F# can be a little bit more cutting edge and try these things out, get them to the point where they're working great, and then the C# and Visual Basic can incorporate some of those concepts as well.
Excellent. And again, you mentioned Axum, which had a cooler name when we first did it on Channel 9.
Yeah, but we always have to map to city names. So.
Yeah, interesting. Very cool. So let's kind of break, the question I have now, people have already probably seen the Mads interview where we kind of went deep into the, specifically what C# is getting out of this and how you use it in C#, right? It's really not rocket science. You have an async, and you can use either a task or void, and then inside of there you're going to use a wait.
Yep.
So that's the complexity, which is beautiful because you guys added a simple way to express complexity, and that's always been Andrew's goal. It's a good goal for the language. What do you have to change in task? Anything?
So we didn't have to change anything.
Okay.
There are things we have added and things that we've improved, but the core functionality is there. So
yes, of course. See,
like
that was the second. Yeah, please. Thank you.
So today, with TPL, if you have a task, so you say var t equals something, we'll just write out task to be clear, and you want to know when this is done, you have a few options, right? So if you're writing more kind of structured parallelism workloads, you might launch a whole bunch of tasks in parallel and then wait for them all to complete. So you might say t.wait. But this is a blocking operation.
Okay.
So for more asynchronous modes of joining with this work, we offer continue with. So you could say t.continue with, which, just as a reminder, takes a delegate. And you have code here which will only execute when the task has completed. You can think of this as an event, as a callback, whatever you want to think, it's a continuation. And logically, this is the only thing that from the await side of things, that the compiler really depends on. So when you say await t, and then you have some code here, under the covers, the transformations that are happening are really signing up this ... as a continuation off of the t. So the core foundational support is there. There are a few things that we're adding internally to the task power library to make these kinds of patterns more efficient.
Okay.
And to streamline them more, because if you know about certain use cases, you can obviously optimize for those particular use cases. But the core support is there. And the interesting thing about this is you don't actually want to, in many cases, bind the language directly to the continue with method, for example. And in fact, the await operation, you may have talked about this with Mads. I haven't seen the video yet, but the await operation is actually pattern-based. So you can await things more than just task and task. A T result, you can await anything that implements the right pattern.
Okay.
And as a result, the compiler isn't, in the await side of things, it's not looking for tasks and continue with, it's looking for this begin await and end await method, or get awaiter and then begin await, end await methods. So one of the things we did add to the library is a method on task called get awaiter, because that's what the compiler actually looks for and binds to. So it's only necessary because of what we kind of agreed on as the protocol between the library and the language. Similarly, when you write an async method, so if I say public async task foo async, and I have some code here, some awaits and whatnot, the compiler needs to know how to create one of these tasks things. And the protocol in effect that we agreed on between library and language, we could have just used the task completion source type, which has methods like set result and set exception and set canceled and so forth. But while the functionality was all there, the API didn't match exactly kind of the contract we wanted between the library and the language. There's also, again, getting back to this concept of some overheads we can avoid if we know exactly how it's going to be used. There's some slightly more efficient things we can do if we want to map directly to the patterns that will be employed by the compiler. So we actually have a type that lives in the runtime compiler services namespace that behaves very much like task completion source, but that provides the exact API that the compiler looks for. And again, the functionality is all there in .NET 4, but we've put this veneer on it that makes it more amenable to what we're doing with async.
Interesting. I mean, it's actually an interesting rabbit hole to go into. Is that, you use the term a couple times now, the protocol between library and language. Because one could argue that you could do this, like everything we've learned, purely in the library. This doesn't have to be a language feature for this to be useful. One could argue. Or one could argue that that's not true. That this is an example of where the library only goes so far, then you have to add these new things to the language, and then the library has to accommodate that.
I think this is a great example of the latter that you just mentioned, where the functionality is all provided by the library, but these control flow constructs that you're used to having in the language are language constructs. And thus, in order to enable this sort of no more callbacks approach and not having to invert your code, because even with task continuations, I still have to break the code that I logically wrote immediately after here. I still have to separate it out into a delegate that exists as part of this continue with call. And if there was a loop here, it's not just this ... I have to separate out. It's somehow this ... plus this curly brace going back around to the next iteration of the for, and so forth. That kind of construct is near impossible to express in a library without building a library that is really sort of its own language, in effect. And so that's really what the language can bring to bear here, is those transformations. In fact, those transformations are very, very similar to what already exists in C# iterators. It's the kind of thing where, if you have an iterator, if I write a method so I've got an iterator here that's going to continually yield values. This is something I could write before the C# introduced this functionality, but I would have to do it by manually implementing my own enumerable and enumerator types, maintaining my own state machine in order to, once I'd returned out of the enumerators move next and current the value 5, the next time move next is called knowing where I left off, starting up again, producing the value 6, and so forth. The same kind of thing with async. I have to know where I left off so that I can kind of come back to that place. And in fact, internally, the compiler is implementing, or I should say compilers, is implementing this very similarly. Because now, I don't know if Matt's talked about this, but for VB, as part of this async CTP, because the mechanics for async and iterators are so similar, VB now also has iterators just like C#.
Excellent. Well, we haven't. You just, we're going to talk to Lucian. Lucian might be sad that you spilled the beans, but
sorry, Lucian.
It's okay, Lucian. Lucian, why can't I get people's names right? Your names are too complicated, man. There's not enough Smiths and Jones. Very cool. I really like that. I like that story. And but continue on. I mean,
so it really is something it's really only something that the language can provide, that the compiler can provide. The functionality is all there to represent any operation as a task, to get the composability that you get with tasks, because once everything can be represented with the same type, you can start building combinators that compose over these operations, or you can start building libraries that consume tasks, and thus any operation that produces a task can work with this.
Excellent.
But this transformation is really what kind of makes async easier.
So let me ask you a question about making async easier. You know Eric Meyer, and his team has done great work with RX. We've talked about it a lot on Channel 9. And of course, this doesn't adopt sort of that reactive model where you're dealing with streams of events, right? Event streams. So what happens when you are using this model to deal with lots of events? For example, like reading a file, the operating system is going to give you it's going to chunk up a bunch of information and shoot it at you. Your job is to take that and deal with it. In this case, for a task, what if I have 500 things I want to do asynchronously. Can I use this model?
Yeah, so let's piece that apart.
If I try to make sense out of my question.
Yeah, no, it's a good question. So first I should say this doesn't replace something like RX, and Eric and his team with Wes and Jeffrey, like they have done an awesome job with RX. RX is solving, I would argue, a different problem. It really is about composition, really rich composition of event streams. Mouse clicks, keyboard events, things coming over the network, whatever it may be, with these, the very rich model that Link provides for coordinating all these operations.
Cool.
And I should mention that integrates very nicely into something like this. Because await is very much pattern-based, you could await an observable just by implementing a few extension methods on top of observable, which I have to believe that within, how many minutes of this being published that the RX guys will jump on and roll that out there. Or you can implement it simply by exposing methods off of observable that return tasks, and then you kind of get the await support for free.
Yep.
So this is a nice complementary thing to the RX rather than kind of a butting heads-to-heads competing.
Sure.
Now, your second question, I think, was around maybe a performance question about what happens when you've got a whole bunch of things that are arriving. Do you really want to do this kind of transformation for every individual operation?
So something's going to shoot at me, a bunch of things, and I'm only interested in certain aspects of what's coming at me. So I have a pattern that I want to match. Loosely.
Yeah, and the interesting thing with here, so let's say we had a loop like this, and the thing we were awaiting was the next piece of data.
Okay.
And typically when you have these cases, you're downloading from a database, for example. The database isn't going to send you one record at a time. It's going to send you them in 100 element chunks or something. So there's a long wait for the first one to come in. But once I've got the first one, I can immediately get the second, third, fourth. Those are all buffered up. Once I get to 100, and then I do 101, then I have this other kind of long delay as I go back to the database and get more data and so forth. So there's actually optimizations built into the pattern that allow us to do that very efficiently.
Okay.
So I think Mads probably went over the pattern slightly, but I'll just recount it for this purpose.
Good.
When you say, let's say I'm dealing with a task of string. So when I await it and I say string s equals await some t, where t is a task of string. This actually gets transformed into something like the following by the compiler. The compiler first calls the getAwaiter method. Just like we had getEnumerator, we've got getAwaiter.
Nice.
No restaurant jokes.
Hurry up and wait, man.
Exactly. So I'll just call this an awaiter. And then the next thing that gets generated is a call to a method on the awaiter. So it looks something like this. So we get our awaiter, and the first thing we then do is call our beginAwait method. Now this move next here is basically a delegate, that's an action that's been generated by the compiler to represent the state machine. Very much like the move next method that's generated on the IEnumerator for an iterator.
Okay.
So this move next method pushes the iterator, the state machine forward to kind of the next thing, running whatever next bit of code was necessary. So beginAwait is just taking an action. And the contract for beginAwait is as follows. It gets passed a delegate, and if the thing that's being awaited has not yet completed, it schedules this delegate to be run whenever that thing completes. This delegate, I mentioned moving this forward, in effect comes back into this method and jumps to this label. So at some point in the future, when the task being awaited completes, this delegate will be scheduled and we'll jump back in here and continue executing, at which point we'll call end await, we'll get the result, and we'll continue on.
Okay.
However, if this task has already completed by the time we call begin await, then this is not scheduled, this returns false, so we don't return out of the method, we just keep executing. So this transformation actually enables you to return, if you already have the data that you're awaiting, because it's been buffered up, you just pull it out of the queue, return a task that contains that data. You no longer have to go through this whole mechanism of posting back, having it run as another task or work item somewhere. Literally, it's just call in, this returns false, keep executing, and you're done. So that kind of makes that pattern very efficient.
Sure.
Yeah.
Excellent, man. And so a question I have as well is, in some sense, aren't you kind of mimicking the behavior of threads? Aren't you sort of like in JavaScript, you can use exceptions to mimic a thread in a kind of a crude way. So really, that's my question. In some sense, you are doing that. You're not creating a new thread.
So a thread
can
have. You can think of a thread in different ways.
Yes.
There's the thread that is the operating system construct that has a stack associated with it, that has a current instruction pointer associated with it, that has certain kernel objects associated with it, and so forth.
Yes.
But thread actually gets its name from this concept of a logical thread of control. The more generic English term thread, not the computer sciencey term thread. We're mimicking that thread of control, not the original thread. So we're mimicking this ability to maintain the same kind of control flow constructs that you're able to write in language, but we're not doing it using an actual operating system thread, at least not during the await points. So while you're saying, basically when you say begin await, and you pass the remainder of the operation you return, you're probably returning to the thread pool, which is going to go process other things. You're returning to the UI message loop, which is going to go process more messages. There's no thread that's dedicated to this operation. When that wait completes, and you end up back here, we are actually using an OS thread as we execute this code. That OS thread is likely the UI thread, because when this completed, if this was on the UI thread here, then when you get to this point here, you want to be back on the UI thread. So this operation posts back the move next to the UI thread, such that we're back on the UI thread. So we're consuming a thread in that sense, but we're really restoring the logical thread of control, not the operating system thread. One of the main misconceptions I think we'll face and really have to educate people about is that when you write async here, you're not telling the compiler to spin up a new thread or to queue a work item or anything like that. You're simply telling the compiler to do the same kinds of transformations that you had to do with iterators. It would be like here if you had to say iterator to enable the use of yield return.
Okay.
Here you have to say async to enable the use of await.
Await. Yep. Very nice. That was a great sentence.
Excellent.
There's a lot of information there.
Sorry.
No, I like that.
So I think your third question, I don't remember it exactly, but it had to do with
Me neither.
How do you operate on a whole lot of tasks being launched, maybe processing them
Yes.
together and so forth. This gets back to one of the original questions you asked, which was what else has been added to the library to help deal with this kind of thing. So one of the really interesting things is that pretty much everything you need to build up higher level operations is present in Continuous. Because what Continuous gives you is this ability to have an operation that's been launched, you get back a handle to it. You don't have to specify a handle up front, like with the APM pattern where you have to hand in the object state and the callback before you initiate the operation. You initiate the operation here with this task-based async pattern, and you get back a task. Once I have back that task, I can call continue with on it to know when it's done. If I'm given many tasks, I can call continue with on each. And I can build up these higher level combinators just like RX does around observables, right? You can have an individual observable, and you can subscribe an observer that knows when it's completed, or that gets pushed a notification when it's completed. You have the same thing here with tasks. So we've been able to build up a set of the most useful, we think, combinators for operating over tasks. So in your example, let's say you had an IEnumerable of strings that represented some URLs.
Okay.
And we just want to download all these.
Mhm.
So if I was writing these synchronously, I might write a link query and say var pages equals from URL in URLs select download page URL, and now here's a to array. So here my pages is just an array of the contents of all the pages together.
Okay.
Now, one of the interesting things about this is I'm obviously downloading these things sequentially. I download one, then I download the next, then I download the next. To your question, if I had 500 of these, I've got a pretty good sized pipe coming out of my computer into the internet's, lots of computers across the internet. I'd like to be able to download them all concurrently.
Yes.
So how do I do that? Well, let's say instead of having a download page that returned a string, I had a download page async that returned a task of string. Okay? So now this is no longer string pages. This is now an array of string, or array of task of string rather,
Yeah.
instead of an array of string. Now I need to be able to join with all these things. So this is one of the examples. We could go through each of these, hook up a continuation off of each one, keep a remaining count of how many were completed. But that's kind of ugly code to have to write. So one of the things we now have with task, and I should mention for the CTP, because we can't add new static methods to an existing type in .NET 4 out of band, we have this separate class called taskx, just kind of a temporary placeholder for these kinds of methods. So when you see me write task, if you go looking for it in the CTP, think taskx. Yeah.
Okay.
But I'll try and write x just when I remember. So here I can say taskx dot when all,
Yes.
and just pass in that collection of tasks. So we already have this method called wait all on task. So you can say, I'll just write task,
Yeah.
because I will forget. We already have this method called task.waitAll. And if you do this, you will block here until all these operations have completed. But if you're writing an asynchronous method, you don't actually want to block until they're all completed. You want to release this kind of thread of control until they're all completed, and then once they're all done, keep resuming. So we have this whenAll, which returns a task. So I can now say await task.whenAll, and I won't reach this point here until all of my operations have completed.
Okay.
Beyond that, what I'd really like to do is get back to the original code I had, which was string pages like that. But here I have this this select download page async URL. So I can just add here await. This is going right here. Task dot when any, wrapping this whole thing.
Wow.
And task dot, when all. That's what I meant.
Yeah.
And when all, because it's being passed a task string array, will return a string array. Basically kind of taking the string out of each thing and giving me back the original thing that I'd hoped for.
Excellent.
So I can just write that kind of code, and there are a bunch of these operations now. You can do things like task.whenAll, task.whenAny. So if I were to do whenAny here, I wouldn't be able to say this, but I'd be able to basically keep executing as soon as the first one of these downloads completed. It's kind of like a choice instead of a join, in effect. We have other methods like delay. So if you were writing an operation and you wanted to say, I've got some code here, and I've got some code here, and I don't want to execute this code until 10 seconds have passed.
Okay.
So if I was writing this with sort of synchronous blocking code, I might say something like thread.sleep for 10,000 milliseconds. But with the async approach, I can say await task.delay for the same value. And now, again, I won't get to this point until 10 seconds have passed, but I'm not blocking an actual thread from the operating system here. I'm in fact returning out of whatever method contained this, and then I'll call back into here, or the language will call back into here when this delay has completed. So when any delay, we have some shortcuts to enable you to very easily spit off a task. So in .NET 4, we have a very rich and powerful task factory start new, which allows you to do things like replace a scheduler, specify creation options, pass in state, and so forth. But often all you want to do is just kick off a task. So we've got task.run, which is just the shortest we could logically make, 8 characters to kick that off. And so we've got methods like this built in, but then you can also go and build your own. So in the CTP, there's a document called the task-based asynchronous pattern, which is walking through the pattern for how .NET Framework APIs will start exposing, instead of the APM pattern, the asynchronous programming model, begin end, or the event-based pattern will start exposing methods that return tasks.
Excellent.
So it walks through what that pattern looks like, and then it also walks through how you utilize these methods and these kinds of operators to build up larger operations, and how you can then also write your own. So if you wanted a retry, if this operation fails, retry it, what would that look like in the sort of normal sequential control flow? And what are the differences between doing it with synchronous code and asynchronous code using these patterns? So it's definitely, I hope it's a good read. And
Did you write it?
I did.
Nice. Excellent, man.
So that's why I say I hope it's a good read.
I'm sure it is a good read. So read that, everyone.
Yeah.
It's important. Okay, so very cool. Now, one of the questions I have next is, and of course Mads actually went over this, but the reason that we're going over this again is because there's a difference between the way that the library kind of thinks about it and the way the language thinks about it, certainly in terms of passion and focus, which is a beautiful story in and of itself. But beyond any of that, a lot of times if I'm doing a lot of things asynchronously, I might want to be able to inspect results at any given time. And so you've also made it easy to do that, I'm assuming. I mean, you understand my question? So in this example, I'm going to want to inspect and maybe match this to some sort of kind of things I'm not interested in, things I am interested in. So I'm trying to say it's all about inspection of my result set.
So there's a few different aspects, I think, to that. One is that at the heart of this all is still the task type. And the task type is really a data structure that stores kind of the key information you care about. It stores your result, it stores your exceptions, it stores its status, kind of where it is in its life cycle and so forth.
Excellent.
With all the beautiful veneer that the language provides, at the heart of all this is still task. So while I can write something as simple as string s equals await download async some URL, I can also, in effect, break this apart into 2 pieces, which is, don't just await it directly. This is giving me back a task of string, or task of sting, either way. And then I can await that, right? Because this is just, await just takes an expression that is of a type of task. So I can say string s equals await t. This is exactly the same thing, but now I have this object that I can inspect. And if you look at tasks even in .NET 4 under the debugger, there's a lot of information we tried to put in to make it easy to understand what's going on here. So tasks have debugger display attributes on them, they have debugger type proxies on them to kind of show the most useful information and so forth. We also, internally, and I don't know how this will actually end up showing in kind of the final product whenever that may be, but we keep track of the methods that you write here. So public async so let's say I return s dot to upper. So my foo function is downloading a page, asynchronously uppercasing it and returning the result. We actually in the library keep track of all of the outstanding operations that haven't yet completed. So if you know, currently in the CTP, if you know the right magic incantation to type into the watch window, which I think I'm going to have to, let's see if I get this right.
Be careful.
I know. System.runtime.compiler services dot async method builder dot debug info dot active methods, maybe.
Amazing, man.
We'll see how amazing it is. We'll post on channel 9 if I got this wrong.
This is where you want to use a using, man. Using async debug equals.
Anyhow, if you were to type this string into a watch window, assuming I got it right, you'll. This is basically just an enumerable of all of the outstanding operations that haven't yet completed, and you'll. Because we're capturing, for debug purposes, we're capturing things like what the current context was when this was initiated, what the current time was, what the current thread stack was, and so forth. And we only do this in debug because capturing all that stuff is expensive.
Sure.
But at least until we have some better UI to expose this, you can at least see that we're capturing the data, and you can use this to go in and understand kind of what are all the outstanding methods. And one of the things that we capture is the actual task, so you can look at the task as well.
Excellent.
So there's a lot of things that have gone into trying to help make this a little bit easier. Now, this is interesting from a debugging perspective, and this is something that the language guys can talk about more, but when you start doing these kinds of transformations, debugging starts becoming interesting. What does it mean to step, normal kind of F10 or F9, whatever, step from here to here? As far as the debugger is concerned, this got translated into something that returned, right? So this actually left the method. What does it mean to step? And so we have some good ideas, I think, about what that actually means, but they haven't been implemented for the CTP. So if you...
So what does that exactly mean? You tell me that I can't use breakpoints in the CTP?
You can.
Okay.
You can set a breakpoint here and it'll be hit. You can set a breakpoint here, it'll be hit. If you set a breakpoint here, you'll be able to step. But when you step past here, you won't ever get to...
Understood, because you left the context of the method.
Right.
Yeah. Interesting.
Once you understand what's happening, it's fairly self-explanatory.
Sure.
But the extra logic in the debugger to know about that hasn't happened yet.
Okay. I mean, in some sense, if you did want to step out there, you could use your nice, big, ugly, unbelievable. I don't know what you'd call that. What do we call that anyway? How would you name that to somebody? That is a sort of an address to a class.
Yeah,
right?
this is a static method.
Sure. Address to a static method.
This is the namespace.
Yeah, that's the namespace.
This is the type, the outer type. This is the nested type, and this is the static method on it.
Yeah,
this isn't really meant to be exposed.
Of course. My point is they could get information there.
Yeah.
And you guys do great jobs of building visualization tools, which people are using for task-based parallelism.
Right, the concurrency visualizer,
Yes.
Visual Studio, the parallel tasks window, and so forth.
So I have a question for you.
Yeah.
Every time I come to Parallel World, I have a sort of a sentimental attachment to CCR.
Yeah.
Because it was the first thing that kind of blew my mind with concurrency and the way that you can, he leveraged iterators back in C# 2.0 time frame, right, to pull that off.
In fact,
Talk to me about what's going on here.
Yeah, so it's interesting. A bunch of frameworks, including CCR. You got CCR. You've got Jeff Richter's Async enumerator.
Yes.
You've got internal stuff. They all kind of leverage this iterator hack and the fact that iterators end up looking very much like these async methods. So this is really almost a
celebration of the iterator.
A celebration of the iterator, yeah. But using the same concept, but exposing in a way that it was intended for. Whereas initially, when iterators were added to C#, there's been some really cool stuff done with hacks around them, but they really weren't meant for async programming.
Okay.
And yet, because the state machine kind of enabled that, people took advantage of it in that way. And particularly with CCR, people have really liked that. It's enabled them to, in a much more friction-free manner, write that kind of code. But so back to your original question. We've worked pretty closely with the robotics team, George in particular, the CCR team, to figure out how to bring a lot of the key concepts from the CCR into the .NET framework, into the task power library, and so forth. And so actually, as part of the this async CTP, we've included kind of an initial look at what this work looks like.
Excellent.
So there's in the CTP a new DLL called System Threading Task. And if you remember, this is the namespace for the task parallel library, .dataflow. So you'll find this DLL, and it contains a namespace of the same name, System Threading Tasks Dataflow, which contains basically a library of support that's very heavily based on both the CCR and kind of key constructs from the CCR, as well as the asynchronous agents library that the parallel computing platform team built for Visual C++ 2010 async agents library. So we kind of looked at both of those systems, looked at how customers were using them, what kind of applications they were building, what were the key patterns that they were using. We looked to see what kind of functionality from CCR overlapped with the task parallel library and vice versa, and other support that has since come into the .NET framework. Since the CCR has been kind of evolutionary over time, and is a lot of concepts that were influenced there are also now in the .NET framework. So we didn't just want to take the CCR wholesale because it would be a duplication of a lot of things. It's how do we take the key remaining components and bring them in.
Excellent.
So we've got this this Dataflow library. And one of the cool things about it, and one of the reasons it's incorporated into the async CTP, is because it's very much focused on tasks and exposing these kinds of patterns in a way that conforms nicely with the C# and VB language support for asynchrony. So why don't we just take a quick tour through kind of like what this stuff looks like. There's also in the CTP, there's a document called Introduction to TPL Dataflow.
Did you write that as well?
I did.
Excellent, man. Wow.
That kind of walks through a high level of what this stuff is.
Okay.
So I'll kind of start with a couple examples, then we can kind of back out into kind of the overall picture of what this thing looks like.
Okay.
One of the most common things that people want to do is they want to send some messages and have those messages processed asynchronously, typically sequentially, but asynchronously. This stock ticks coming in. You want to pass them off to have another thread quickly evaluate them, but you don't want to spin up another thread to be blocking waiting for work, because you might have 1,000 of these things or 10,000 of these things all receiving messages. You don't want to have 10,000 threads. Yeah. So what you typically want is some kind of buffer to store the data. You want some sort of manager to spin up tasks when there's data to be processed, process that data, and then when there's no more data, the task can go away until there's more data. So if you think about all that kind of buffering and processing, you end up with this type called action block. So here I can say AB equals new action block. Let's just pass in integers. And here I can do something. I can process I. And now I've set up my computation. So my computation is to process all messages that arrive. And at some point later, again taking the nomenclature from the CCR, I can post values to this, and so forth. These will end up inside the action block, and as soon as we post these values, action block says, all right, I have stuff to do, and it starts spinning up tasks to process this data. When there's no more data to process, the tasks go away. There's a lot of customization you can do here. This guy takes as a parameter a data flow block options, which allows you to do things like control where this work actually runs. So maybe I'm going to use this to post messages to my UI thread, in which case I can pass a task scheduler here. This is all based on the task parallel library. I can pass a task scheduler that will run the work on the UI thread, or anywhere else I have a task scheduler to do it. I can control how many messages are processed at a particular point in time. So by default, this processes messages sequentially, which means that in here you don't have to worry about locking, things like that. It's all sequential but asynchronous. But if I wanted to, I can say, you know what, I really want you to process 4 messages at a time, or up to 8 messages at a time, and kind of get my parallelism internally to the block. I can say, I can cancel this, so I can pass a cancellation token into here, and then if I cancel that token, all processing that's monitoring that comes tearing down, and so forth. Now, there are other blocks. I should mention actually that one of the ways this ties in with this async language support is you'll notice here that I'm taking a deli. Let's say this wasn't int, but this was string,
Okay.
and this was posting URLs to it. And here I'm downloading a page, URL, and I'm getting back a string, and then I'm doing something with that string. And so every time I post a URL here, it'll download it and process the download. Now if I want this to be asynchronous, I can say, add that async keyword that we have for the language support,
Yep.
await, async, assuming I have another overload that returns a task. Now it's exactly the same, except the action block is now running this whole thing asynchronously. And again, when a message arrives, it'll start processing. When it hits the first await point, it'll stop processing. It'll release all of its tasks and so forth, still maintaining the degree of parallelism, still maintaining the ordering that these blocks implicitly provide, and so forth, and it'll resume again as soon as that operation has completed. So this kind of incorporates again from the CCR this notion of these iterator tasks that the CCR had, but building it in a way that incorporates the first-class language support.
Interesting.
Another way that this merges with the async support in the language is I can do things like, let's say I post a whole bunch of values, post 1, 2, 3, 4, and so forth. At some point I may be done, and I can say ab.decline permanently, however you spell that, which basically tells the action block you're not going to get any more data. At that point, I could say await ab.completion task. So there's a task off of all of these data flow blocks that represents their complete asynchronous processing. So now when I await AB completion task, again, if this is within an asynchronous method, I'll get out of that asynchronous method until the block has completed processing all the data that was posted and buffered to it. All of the asynchronous processing in here is all done and so forth, kind of this big compositional nature.
Excellent.
So some pretty cool stuff, and this is just one of the 9 or 10 blocks that are actually part of the data flow library. And this is an example where it represents a very common pattern. In CCR, this would be basically a port that you attach to a persistent receiver to.
Interesting.
So if you want to, you can still build up, you use these kind of core primitives to build up these larger systems like you do in the CCR. You have these smaller primitives in the port and the receivers and so forth. But we have tried to encapsulate the common patterns of, for example, action block. So this is an example of something we call a target. So an action block of T is a iTarget block of T. Basically something that you can send data to.
Okay.
We also have iSource blocks. And in fact, many of our blocks implement both of these. So you have these things we call propagators where you can send data to them, they do some processing, and they send data along from there. And with this, you can build up networks of these data flow blocks. So for example, we have a block called transform block. If you're familiar with asynchronous agents from Visual C++, you might remember this as call of T and this as transformer of T.
Okay.
Or transformer of T1, T2, or whatever we call it. So a transformer block is both, basically this is T input and T output. And it is a iTarget block of T input and an iSource block of T output. And if you're familiar with link, you can think of transform block as being kind of like select. So you send in inputs, it transforms them, and it has outputs. So it's a target block where you're sending it inputs. You give this guy a function that takes the input to the output, and you can then have the output. If you look at this as kind of a diagram of what the data structure looks like, it's basically an input buffer here, some number of tasks that are running the function that you supplied to process this, and an output buffer. And so messages kind of arrive into here, they get processed, they end up here, and then you need some way of getting them out. So with sources, you can receive from these blocks in any number of ways. You can just call something like try receive, which is just a very quick operation. It's got out T item, and it returns a bool. And basically, it just checks to see whether there's anything in this output buffer. If there is, it gets it. If not, you don't get it. And that's sort of the very simple way. But you can also do things like integrate this with the asynchronous methods. So, for example, if I had one of these sources, I could sit in a loop while true and say t next value equals await s dot receive async. So receive async off of the source is giving you back a task of t. So now when I await this, we're basically waiting for some data to show up here, be processed by this guy, shoved into this output buffer, and then that data being removed from the buffer and returned to my basically asynchronous consumer here that's sitting, pulling data out. This ability to kind of register for notification when data is available is actually a lower level support provided by the source block, which allows you to link blocks together. So if I have a source, I can connect a source up to any number of targets. These targets may in turn also be sources, for just like transform as a target and a source.
Okay.
So that I can connect this guy up to any number of other. So you can build up these data flow networks where data is propagating through these linear or nonlinear pipelines, where each of these blocks may individually be processing sequentially, but all up, you've got a lot of concurrency here because they're all processing concurrently with each other. And if you wanted to, then individually these could all internally also process in parallel.
Awesome.
So then things like receive async are just built on top of this ability to link blocks together. And this is done, in this case, just by saying s.link to t. And you basically have a link established where now if data arrives here, it'll automatically be propagated out with, again, a protocol for how these things communicate. These guys can choose to decline the data so it remains in the source. They can choose to be greedy or non-greedy, so you can do things like the CCR has this concept of basically data arrives on a port and it gets, you can have a joint receive where a particular operation can monitor multiple ports for data to arrive and remove from them atomically. This protocol allows you to do the same kind of thing. So if I had multiple sources here, this guy could be written to say, I only want to take the data that was offered to me from both of these when the data is available at both. And in effect engages in almost like a database transaction, a two-phase commit in effect to say, can I have this data? Are you sure? All right, you've now committed it to me. Can I have this data? Are you sure? Okay, you've now committed it to me. And only when they both have, kind of taking it out and so forth. So this is a lot to take in, I know.
Yes, but it's very, very interesting.
And it allows you to write some very concise but interesting problems where you're expressing them much more as the flow of data rather than kind of the flow of control. And to integrate it back with the control flow world through things like the language async support.
Yeah, really, really interesting. So, we've got to wind down here, but so this will be the first time people get to play with this. One of the questions I would have, if I've already made applications that take advantage of task, and I've taught myself, how to use task or task-based parallelism, it should be pretty straightforward for me to just kind of move my mind more towards the asynchronous side of the things.
Absolutely.
But as you just mentioned, one of the things about the CCR was it's only simple in name. There's a lot of things that you just mentioned with the data flow kind of architecture, so my mind is kind of hurting a little bit right now. But I think we didn't talk about this with MADS. This is very interesting in how you put this together with async and await. I can see some very interesting scenarios. The last thing I have to ask you is more of a human thing. What were some of the hard problems that, you guys come from library world, and you're spending a lot of time thinking about parallelism, as you mentioned. This is the result of several different projects.
Yep.
You just talked about CCR,
CCR,
which is specific.
AXM, asynchronous agents, the whole capability.
Cool. So there's two questions for you. So the first question is, what was sort of the hardest problem you guys had to solve together as a unit? With you going to the language team meetings, sitting down and being like, all right, You have the protocol. What? Talk to me.
So I think the biggest gap is, and I should say it's been a pretty awesome experience. The teams have gelled really well together, which is something that's, I think, rather unusual. You would hope it wasn't, but
Yeah.
you know, cross-group collaboration is always, people have their own agendas, and this has worked out very swimmingly.
Excellent.
But there are still different opinions on how things should operate, and I think one of the biggest differences has been from just the pure library versus language perspective, and the kinds of things you need to take into account, who your target audiences are, the kinds of scenarios you expect people to be using, and so forth. So from a library perspective, we've always been very cautious. We're very conservative, in effect. So if something can go wrong, we expect it will. We always have the little knob to allow you to kind of escape from some behavior if you don't want it. We want you to observe all your exceptions and all this kind of stuff. We expect that you're willing to take a little bit more pain, I guess, because you're working at sort of the library level, and you're just controlling what these data structures and objects do. At the language level, it has to be kind of drop dead simple, right? So the decisions you make and how you incorporate things into a language as a language construct, they're a little bit higher level.
Sure.
You don't want that complexity exposed. At the library level, we don't necessarily want it exposed. We feel like we have to. At the language level, you just can't. Right? It's not an option. And so there are discussions that happen around, well, how do we expose this piece of functionality in a way where we can still expose the functionality, but sacrifice some of the control you would have at the library level, yet still not sacrifice the usability or the functionality that we're trying to provide by doing it through the language level. So an interesting example of that is, I mentioned exceptions. In .NET 4, we're pretty draconian when it comes to exceptions with the task parallel library. We have this whole scheme where if you call some function, and this function has an exception, that shows up on the resulting task. So if I say t.wait, that exception will be propagated to me. If after it's done I see t.exception, I can see what that exception was. In the language, with this new language feature, I can say await t, and I kind of asynchronously await this object. All of these cause me to, in a sense, observe this exception that was captured into the task. We can't just do what happens with threads or the thread pool and just let the exception propagate all the way out of the call stack and crash, because we need to marshal it from this asynchronous kind of world over here back to this future point in time when you may actually wait for the operation, get its result. If I call foo async and I'm awaiting it, I don't want to crash the process. I want to get the exception kind of propagate just as if it was the synchronous call. But let's say I never actually do this. So if I never actually observe the exception, now I've kind of thwarted the support that I have with threads and thread pool for crashing immediately when an exception occurs. I'm never seeing my exception. And so in .NET 4, we had this scheme where if you never observed, once we knew that you never would, meaning the task got garbage collected basically, we would then rethrow the exception on the finalizer thread, forcing you to see the exception and crash your process, out of concerns that if you let the process run too long, bad things may happen, and so forth.
Yes.
But from a language perspective, that kind of leads you down to the pit of failure rather than the pit of success. If I'm with tasks and just using the library, you kind of had to know that you were in this world of parallelism and concurrency. But if in the language I can just say var t1 equals foo async, var t2 equals var async, await t1, await t2. This was very easy code to write. I'm not really in the mindset that I'm employing parallelism or concurrency and that I might have to deal with all this stuff. And yet, if both T1 and T2 failed, this will throw an exception because I'm awaiting the first guy, and then I'll never await and thus never observe the second guy. And so this is kind of this pit of failure that at the language level we have to think about. So what we're looking at is kind of making it optional, in effect, whether to employ that same .NET 4 draconian exception crashing behavior, where maybe by default we wouldn't crash, but we allow you to get back that behavior for debugging, for testing, and all that kind of stuff.
Or you could take, I mean, let's be honest, take the VP, I mean, you could take the VB approach. Can you imagine doing that? So, option explicit. You could have option exception explicit or option whatever, where you have already informed the system
Right.
that
That
you
you
want
care.
draconian.
Yeah, exactly.
Or you say, I don't. And then you warn people at compile time, like, you're going to be releasing this to the wild, and your users could be screwed.
Right. So there are a whole lot of ways that you can kind of make someone choose between
Sure.
them.
Better
But
than
yeah,
forcing them.
It's that idea. So these are the kinds of issues that we run into when you're thinking about it more from kind of a library perspective versus a language perspective.
It's really interesting. So, in some sense, from the the vocabulary of a language, which the language guys are thinking about with async and await, to just really rich set of functionality that you guys have in the library.
Right.
So.
We don't want people falling off a cliff. In effect, when well, I should back up. It's if you have one of the coolest things I think about await
Yes.
is if I have a synchronous method. Let's take just copying one stream to another. That's
Okay.
an example. So I've got a buffer here, and I've got a counter bytes read, and I'll basically say while it's read equals source dot read buffer 0 buffer dot length. And if this is greater than 0, then I'll just write to my output destination.write buffer 0 bytes read. Kind of a very simple read write read write read write. If I wanted to asyncify this with the language support, I can say await async await async. So now I have the async version of my copy stream to stream. And you'll notice that for this one operation, I haven't actually introduced any parallelism. I haven't actually introduced any concurrency. I've introduced asynchrony, but I'm not doing more reads than I was previously doing at the same time. I'm not overlapping my reads and my writes. Just by changing all of my synchronous calls to asynchronous calls, I'm not actually introducing any parallelism or concurrency, and I'm not having to introduce the complexity that results. So from a language perspective, we've now made it really easy to kind of come to the precipice where you're now using these constructs that would allow you to go parallel and allow you to go concurrent. But for this one operation, you're not yet. However, changing this code to one where that would overlap reads and writes is just one or two more lines of code. And so it enables you to take that little minor step. And if you fell off a cliff, that would be bad.
Yes. Let me ask one quick question. I mean, we are going long. For
Sorry.
those of you that are still watching, rock and roll, man. You guys are troopers. But, a lot of people are still watching.
I appreciate
But anyway, plus we have new things on Channel 9 where we can link into specific places. You
Oh,
can
cool.
pause it and save it. When deciding to use, actually, I don't want to go down this rabbit hole because it's going to last too long. My final question is native. I mean, typically, when you guys do things in this group, you don't just think about managed developers. How is this, or is there thinking about how this may move to the native world? So native will get an async, native will get await, or something relative to that. Does that matter? Is it needed?
I think there's thinking about it, but
Okay.
it's not first and foremost on people's minds right now.
Right on.
And so, managed is definitely the first kind of foray into this first-class language support.
Sure.
We also, I think, I don't want to speak for the C++ team or the C# VB teams, but from my perspective, kind of looking on it,
Yeah.
we have a lot more leeway where we own C# and Visual Basic, and we don't really own
Got
C++.
it. Exactly. You'd have to go in to the council. Herb Sutter would be up there lobbying it and stuff like that. Anyway, just kind of random talk. Excellent, man. So thank you for this very good introduction.
Thank
or,
you.
Sort of deep dive.
Sorry for going long.
Hey, there's no problem. I never have a problem with going long. We'll see what, people... Hey, if you're still watching this, welcome. So we'll see you at PDC.
Absolutely.
And this is actually airing at PDC, but probably before you get on stage. I think it's on day 2. I could be wrong. On Channel 9 Live. So
But
we'll
watch
see you
it,
there.
come send your questions, send your
Yes,
feedback
totally.
on all this stuff. We want to know about it.
Absolutely. Take care, man.
Thanks a lot, Charles.